So hello, everyone, and welcome to our June SERC Talk. It's the third talk of the year and the final of our three-part Applying DevOps to Complex Multi-Organization System series. Our next upcoming series will explore distributed autonomy. And for those joining us for the first time, I'm Mimi Marcus, the SERC Talks webinar coordinator. I hope you find the discussion beneficial, and we encourage your active participation. So since we've migrated to the Zoom webinar platform, there's some pointers on the tools. As Barry noted, there's a way that you can view the participants. There's also the question and answer module. If you have any questions during the session, please enter in your questions there. But following the presentation, there'll be 5 to 10 minutes dedicated for that. Anything that wasn't addressed during the presentation. And if you'd like to ask your question directly, I will queue you up to allow yourself to be unmuted and ask your question directly and more thoroughly. Otherwise, I can just read them off to Dr. Mayner directly. And for our participants joining strictly through the phone connection, please note that the slides are up on the SERC website, circuarc.org/SERC-talks, so you can follow along. Dr. Mayner will be noting the slide number that we're on. And you can email your questions and comments directly for inclusion in the discussion at circtalks@stevens.edu. So it's my privilege to introduce Dr. Barry Boehm, not only the SERC Chief Scientist and Principal Investigator of the ILTE's Trade Space and Affordability Project. It's a multi-year research task coordinating many of our collaborating institutions, but also our SERC Talks Editor-in-Chief. Dr. Boehm will be leading our discussion at the end of today's presentation, as well as introducing our esteemed speaker and the talk. So I turn it over to you, Barry.
Okay, thanks, Mimi. So today we're very fortunate to have Dr. Steve Mayner, who is a SAFE Fellow and a Principal Consultant of Scaled Agile Incorporated. His 30-year career in business includes roles as Vice President in multiple Fortune 500 companies, CTO for a health startup company, but more recently he has been spending most of his time helping large organizations as well as the U.S. federal government in how to capitalize on Lean and Agile and DevOps approaches for complex systems. So it'll be clear during his talk how many different kinds of organizations he's been doing this for and how it works out with them. So Steve, we're looking forward to your talk.
Thank you very much, Barry. I'm glad to be here. Thanks for the invitation. All right, and with that, are there other slides here that you wanted to cover before I dive in?
Nope, just our disclaimers. Feel free to get started. Thanks.
All right, fantastic. Well, welcome everybody. Thanks for attending. Again, my name is Dr. Steve Mayner, SAFE Fellow with Scaled Agile. What that means is I have the privilege of getting to write our framework and courseware with the collaboration of other fellows and in cooperation with many of the largest organizations around the world, both in the private sector as well as the government sector. And so a lot of what you're going to hear today is a reflection of many of those collaborations. And I'll point you to some resources where you can follow up for further study and information after the presentation, in addition to the presentation deck itself. Quick introduction for those who may not be familiar with Scaled Agile on the phone. So Scaled Agile is the company that provides SAFE, the Scaled Agile framework. And the framework is basically a collection of success practices. It's a database of patterns that we've observed in very large enterprises for applying Lean, Agile, and DevOps practices at scale in very complex, often high assurance types of environments. It's completely free. If you go to the website on page 4, scaledagileFramework.com, you'll see a big picture there that's clickable and has many articles that you can use to learn about these patterns that we have observed. On slide 5, you'll see that one of the things I'm very proud of, having spent about 15 years working with the federal government, is we're seeing a lot of these patterns now being adopted all across the federal government in small IT programs all the way to large weapon systems programs, satellite systems, and weapon systems, and all kinds of different cyber physical systems. And since that's the talk today, I wanted to mention that adoption is continuing to grow. We're very, very excited about that. The real question that we are here to ask today, certainly lean and agile practices is not a new conversation. It's been around for many, many years, and most recently, particularly with agile, is typically thought of as something that applies to software systems. You think of Scrum, you think of Kanban, you think of where the agile conversation is normally raised. That's usually the context that people think of it as. But we're seeing more and more recently is very large organizations that build things like, as I mentioned, everything from fighter jets to commercial jets, telecommunication systems, automobiles. Can this actually work? How do you do some of the things that are described in Lean, Agile, and particularly DevOps, like a continuous iterative development cycle, when you're actually dealing with physical systems, when you're bending iron, when you're having to do the mechanical side and not just the logical side of that's reflected in the software. So that's what we're going to talk about today. So on slide 7, if you just give you a couple of references that I used to build this presentation on the framework at Scaled Agile. If you go to the website that I gave you earlier, you'll see this picture on slide 7. That's what we refer to as the big picture. It's the navigation tool for the framework itself, and every icon is clickable, and there's an article behind that icon that describes that particular artifact, process, role, in applying Lean and Agile and DevOps at scale. The area that I have in red outline on the picture is what we call our large solution level. And this level contains many practices that I will describe today, and it was specifically added to the framework a few versions ago. Once we started working with some of the very large systems integrators, mostly that work in the government space, who raised some challenges or limitations with our previous guidance, that it didn't quite deal with the level of complexity that you deal with physical systems. And so some of the things that you see in that level now are a direct reflection of working with those large companies, finding out what patterns they were using that were successful, and then writing that back into the framework. The other reference that you see on slide 7 is a white paper that was developed last year with a group of people that are brought together annually by Gene Kim, who's the author of the Phoenix Project and the DevOps Handbook. Anybody in the DevOps space is very familiar with Gene. And he brings a group of leaders together every year, and we break into groups. And in the particular group that I was in last year, along with our founder, Dean Leffingwell, and some folks that many of you are probably familiar with, some like Robin Yemen, who's also spoken in this series. We're also a part of that group. And our mission was to write a white paper that really tackled this question of how do you apply the continuous development and deployment kinds of practices that the DevOps community has been recommending for some time, and how do you do it when you're dealing with cyber physical systems? And we had a group of people there in the group, like Robin and others, who had hands-on experience doing this. And so those are some of the voices that contributed to this white paper. And so the outline that you see in this presentation is drawn specifically from an amalgamation of these two resources that you see on slide 7. And the white paper, by the way, is easily accessible. If you just go to the IT Revolution website, there's a place where they store their white papers there, and they're downloadable for free, so they're very easy to access. So on slide 8, this really is the framework. It's the outline of the 10 practices that we have observed that are essential if you're building physical systems and you want to apply what in the white paper group we affectionately referred to as industrial DevOps, is the best term we could come up with. If you want to deliver differently, instead of the big bang, many years before you ever see something that you can actually test or validate, if you want to do those in a more flow-based, in smaller pieces, so you can evaluate and test and sometimes pivot as you go along, as you gain learning, how do you do that? What are the practices that you need to employ? And so on the screen here and on slide 8, for those who are remote, these are the 10. I'm not going to walk through them on this slide because these are the 10 things that we'll cover throughout the rest of this presentation. So let's dive in. We'll begin with the first one, which is visualize and organize around the value stream. Now, again, value streams are not anything necessarily new, and it's not something that we at Scaled Agile invented, but we are seeing, particularly in the DevOps community, a very strong emphasis on, if you want to apply these practices, the first thing you have to do is think about how we're organizing the people who are working on building our solution. Now, traditionally, and this is, everyone I'm sure on this call is very familiar with, traditional organizational design and what we've dealt with in the past is organizational around function, vertical silos that specialize in an area, and a solution basically has to pass through each of those silos. And doing so in kind of a waterfall, stage-gated, handoff kind of process, what happens is you get all kinds of dependencies and handoffs and dropped balls and things that just are not conducive to flow. And besides, you really don't have a complete thing until it crosses all those silos. And so that adds lots of delay and lots of lead time into getting a solution. The alternative approach that value stream thinking promotes is that you want to get all the people together that are participating from those various silos in the building of the solution to actually be able to work together in a cross-domain, team of teams kind of process. It's probably a virtual organization, and not too many organizations are yet actually reorganizing in value streams, but it's a matrix kind of process where the people that need to plan together and design together and build together and integrate together and test together and validate compliance together are actually able to do that as a matter of course by being able to work together by how they're organized. So what that looks like in SAFE, we talk about the concept of an agile release train. It's just our term for a team of teams. So you've got many agile teams that have different disciplines, and they come from different parts of the organization, as you see on this slide 11. So you've got the software engineers, you've got the systems engineers, you've got the mechanical engineers, you've got fuel systems engineers, you've got all of the people that are part of the solution that are able to have ready access to people on other teams and other domains as they're going through the process of building that component or building that capability. And so what in essence what this is doing is it's cutting out the delay. It's cutting out the waste time that we see in traditional processes where people have to wait to get an answer, to make a decision, to come to a consensus on how we're going to build a certain thing. And so by having those face-to-face conversations and predictable ceremonies and events in our process model that allow these people to work together, we're going to cut out a lot of that time and a lot of that waste. And this process has been working in many organizations for years and years. We're now seeing it applied in physical systems and well. And while it looks differently, certainly, it has the same benefits of cutting out a lot of that waste time. Certainly when we're building something very big and very complex, like a fighter jet or a satellite system or an autonomous vehicle, you have more than one of those teams of teams. And so that's another fractal. It's another level of complexity that we see in really big systems, is that not only do you have teams of teams, but you have teams of teams of teams working on major subsystems and components of a total solution. And so what you see in our practices at that large solution level describe how do you manage something at that scale, where some may be part of the main organization, be it the government, be it the prime supplier, or maybe it's a black box supplier, somebody that's supplying a key component, but they're kind of delivering it as is to the system. And when we're not sure exactly how their work processes are managed, how do they integrate into this new way of working? How do we set expectations for what they deliver and when they deliver it, so we can still have this continuous flow of value? And those are what we describe in the large solution level. It's organizing together so that everybody has the most ready access to all of the organizations and personnel who are part of building the solution. So I'm going to move right on because we've got a lot of ground to cover. The second concept is to apply multiple horizons of planning. So on slide 14, what this describes is in typical Agile fashion, you have planning horizons that are pretty short term. If you're building a software system, you'll hear people, especially if they're using something like Scrum, talking about 2-week iterations or sprints. Teams might have a daily cadence of touch points daily to measure progress. In SAFe for a long time, we've talked about the team of teams, the ART, which works in a program increment, which might be 8 to 12 weeks time box, so that we have, again, a predictable checkpoint that we're going to integrate and check progress. But even at that scale, what we find is that when you're building these very, very large systems, you need even longer planning windows. You need planning windows that can go out years and have roadmaps that describe what major parts of the system are being delivered when, because there are major parts of the organization, external organizations, that have to plan their contribution to the overall solution. Some of these things take a very long time to develop, and so knowing when they have to have their piece ready to integrate with other pieces of the system is a really, really important part of the process. And so one of the things we add in that solution level is this notion of having longer roadmaps that are forecasts of when major parts of the system, we refer to as epics, they're pieces of capability that are added to the solution, when those are forecasted to be delivered and what some of the dependencies are there. Certainly those are, because they're forecast, that means that they're not committed yet, because we may have learning along the way that changes that forecast, right? Especially if we're building something truly innovative, unique, we've never built before, we may uncover learning. This is R&D. And so, the parts that precede another part may turn out looking differently than what we thought, because the reality was different than the hypothesis. And so we adjust that roadmap as we go along, as we move forward. The closer we get, the more specific and committed those forecasts are going to be. And so this slide 15 just reflects that as we go through each increment of development, we want to make sure that we're wrapping the knowledge, wrapping the learning back into both the specifications, because those may change. That's one of the big differences in a Lean, Agile, DevOps approach, is it recognizes the reality that if we're building something we've never built before, if it's true R&D, we'll start off with a set of designs and specifications of intent. But as learning happens, as the reality of the experiments say that, hey, this didn't work the way we had planned, we need to adjust the specifications and downstream items to reflect the new learning. So it creates that picture of that cyclical, iterative learning process that is the hallmark of Lean, Agile, and DevOps. And so we still have to do that. We have to figure out, how do we weave that into the process even when we're building physical systems. So we'll move on to the next one. The next principle is we're going to base decisions on objective evidence of system state and performance. So on slide 17, this is, again, one of the things that I often have heard as I've worked with customers in this space. Well, it's fine to say you're going to deliver a story or a feature in a short period of time, because, well, if you're just doing software, those are ones and zeros. It's very easy to write code and compile it and test it and delivered. It's quite a different thing when you're building some of the very large vehicles and physical systems that we build. So we don't see how this works for us. And certainly that's a very logical argument. It makes complete sense. What it requires is it requires us to think about how the system iterates a little bit differently maybe than you would if you were just doing a pure software project. So the spirit of this is we want to shift away from our previous pattern of, well, everything was just based on a document. We're going to write lots and lots of documentation and consider progress as, well, you know, we got a better specification or, you know, a better requirements document. And so that's, you know, that's somehow proof that we've got a working system. Well, we don't really, we just have some documentation. What we want to do, and frankly, I think systems engineering has been doing this well for decades and decades, is you have to model things out. You have to start, in some cases, as the graphic here, what I intended to show was, is your deliverable thing may be, hey, we figured out the math. And in my classes, I love referring to the movie Hidden Figures because I just love that scene where they finally got the math that helped NASA understand how we knew how we could get a human being up there. We just didn't quite know how we were going to get them back in one piece because we didn't know the math. And so the math was a big, tangible piece of the total solution. We had to have that before we could build the rest. And so if you rethink about the smaller pieces that we're delivering, sometimes it could be math, sometimes it could be a model, sometimes it can be a CAD/CAM drawing, or it could be you know, a board mock-up of a particular circuitry design. We can actually do those things. We can test those things. We can get, you know, this board to talk to this board and see if is that working the way we thought it was going to work. Now, certainly it's not the final system, but remember the key here and the whole ethos of the Lean Agile process is recognizing that we have to learn our way to a solution. So what do we have to learn? What are the smallest pieces of things that we can build to gain that learning so that we can test the hypothesis, prove it or reject it, and then create the next experiment and keep moving forward in the system that way. And again, I think systems engineering has done that very well for a long time. Maybe we're using some new terms here, but I think the two bodies of knowledge of Agile and Lean and DevOps and systems engineering are actually more synergistic than maybe a lot of people have given them credit for. So that's what we're after: fast feedback, smaller pieces of learning. And the other benefit here is that because we're doing these in small batches, if we find something's not right, many times we'll have assumed or have thought that this was going to work a certain way. This component was going to integrate with this component. And when we actually tried it, we found, oh, that's wrong. That's not going to work. Well, if we catch it when we've only invested in a small batch, the cost of change is small. And that's a huge benefit. And not only that, we haven't built other parts on top of the faulty part. So the longer that defect is allowed to go downstream, we all know the greater the cost of that change is going to be once we finally catch it and correct it. So smaller batches is absolutely critical. We want to test that progress with objective milestones. Again, it's not asynchronous checkpoints based on some project plan or IMS. It is in Lean and Agile and Safe, we talk about we're going to have a predictable cadence. Every so many weeks, we're going to force the pieces that integrate to integrate, and we're going to see, can they actually work? The parts that we've said we will have built by now, where are they? Can we test them? What evidence do we have that the piece that we've actually built meets the fit for use and fit for purpose for which it was designed? We're going to do that in a very predictable way, and we can demonstrate what we've done. We can measure. We can get feedback. We can ask the customer, does this look like it's going in the direction you want to go? And we can make adjustments based on a relentless improvement process, which is also part of Lean, with every one of these milestones, so that, again, when we're early in the cone of uncertainty, we're going to make these adjustments iteratively so that we don't end up way off target when we get to the end. Let's talk about the next concept. This is on slide 20, and this is architect for scale, modularity, releasability, and serviceability. So the idea here is, and I really appreciated this conversation when I attended the SERC conference that Barry held last year that he invited me to, and heard from many of the other speakers, a lot of working in space systems, talking about if we want to shorten the lead time to get these delivery vehicles in operation and able to increase the speed at which we can deliver new things into orbit, sometimes we actually have to re-architect the system itself. We can architect with this intent of, I want to be able to build it in smaller pieces. I wanted to architect in a way where I can gain rapid learning, where I can integrate more frequently, where I can automate a lot of things. So what do we see? How do we see this move to DevOps affect architecture? Well, a couple of main things. One, we see lots of modularity and decoupling. And again, DevOps didn't invent that. We've thought in systems engineering about modular plug and play kinds of systems for a long time, but this becomes really, really critical. It allows us to swap out one piece of the system without affecting other parts of the system, and thus have it, reinstantiating a very long loop for testing and recertification. The other thing a trend that we see is not only modularity, but also moving more and more capabilities into software. Things that used to be coded in, if you go way back into actual analog mechanics, then it went into firmware, and now we're seeing that go into software, because if it's in software, we can gain some speed. We can automate things. We can automate testing. We can automate some V&V steps. We can automate security tests. We can do a lot of things much faster by having sound test scripts that we can run infinitely, and it'll always run the same way. Things that are much harder to do when you're doing with testing a physical system. So that's one of the ways that we see as a critical component, is that re-architecting. So decoupling components, so independent modules, as I mentioned on slide 21. And what that also does is it enables the more decoupling you do and abstraction you do, that also allows the teams and the teams of teams that have a responsibility for that module to build, test, deploy, and potentially even release components of that system more frequently and independently from a larger monolithic release. And if you look at I love reading what's going on with Kessel Run and some of the Air Force systems that they're working with up in Boston, because this is exactly what the metaphor that they're working against, is to take modules of the system and be able to architect them in such a way they can release them independently and more quickly, rather than doing the massive large block upgrades that can take years and years to get new capabilities to the field. Now, not all systems are going to work that way. Some things are still going to require that physical replacement of a component. But what this does allow you to do is think of a system in terms of different releasability capabilities within that system. So some things that are in software can be released very frequently. Some things that might be more asynchronous, maybe it's a security patch or something like that, you can release on an as demand, as needed basis. Some things may be a little more hard to release. We don't have to physically get to it, but maybe it's a very complex kind of release. And so we want to do that very carefully, and because some parts of the system haven't been completely modularized, and so there's maybe some fragility there. And then, of course, there's always going to be, in any physical system, there are just going to be some pieces of the system that are more traditional release process, because there's a physical component that you have to swap out. But it does give us more options than we may have considered that we had in the past when we architect with this this type of flow of new capabilities in mind. Next, we'll talk about managing the supply chain with systems of systems thinking. So inevitably, when you're dealing with a large physical system, like in this case, I used a fighter jet, you think about the suppliers, the number of organizations involved. So you've got different contexts that may involve different suppliers. You've also got different components of the total solution that are going to involve different suppliers. Some of these may be entire value stream portions, trains within the prime contractor. Some may be an external supplier, as I mentioned earlier, that's just providing kind of a ready-made piece of the solution, perhaps like an engine. The key that we have found to achieving DevOps and continuous flow across a complex system like this is getting all of those parts of the system of systems working on the same cadence and aligning those cadence. Because the key to making all these work, and everybody on the phone has enough experience to know this, it's developing the thing that you're building, whether it's a communications component or a piece of navigation software. It's not the building it, it's the integrating, it's the testing, it's making sure that it works and plays well with all the rest of the system. And so we want to make that a very disciplined, predictable process for when those integration points are going to happen, no matter who's involved. So yes, there are some complex coordination that goes on here, but when it's predictable, that's the key. You set the cadence and you say, these are the very predictable points at which we're going to force the system to integrate together. We're going to test those integrations, and we're going to know the state the system sits in as of that point in time. And we're going to take that learning and only plan the next increment. So we're not getting too far ahead of our skis. We want to validate the next piece as well in the same fashion. So this is the way we iterate and sprint the system forward, if you will. The complexities that happen here is because you've got so many systems and subsystems, and some systems are part of a larger system. There's kind of this nested supply chain process. One of the things that we describe in solution in large solution layers, this concept of solution intent, which is that repository of all the artifacts, all the data that reflects both the current state of the system and all of its subsystems, as well as the intended future state as far as we've designed it, and both where the parts of the system are fixed. It means decisions have been made in terms of this is the actual component we're going to use, it's the design we're going to use, and where there is still variability in the system. Where are we still discovering things? And it's very important to distinguish those because of this complex nested chain of relationships, because the vendor that's supplying the overall avionics system is dependent on what that radar supplier is doing as part of that solution, which is part of the overall solution. And so having some way to track all these things is really, really critical. These kinds of systems have been around for a long time. They're legacy systems, but they haven't always been designed to work in flow with this variability factor. A lot of them were historically designed to fix everything up front. And of course, we know that we can't know everything up front. And so we end up with massive change orders and lots of confusion. And so my recommendation here is to really look for modern repositories. And they're out there. We have partners that do that, specifically designed to use safe language, to make sure that everybody has this common view, this common repository of where the system is and where it's going in what we call solution intent. The next concept is iterate and reduce batch size. I've alluded to this earlier. So in slide 27, it's just a very simple comparison of historically we go through the stage gate waterfall type of process. It's not evil. It's the best it was at the time, but the pace of change and just the environment that we work in, the markets we work in, the battlefields that we work in are requiring much faster cycles of delivery. And so the key is we're going to shorten those batches of learning. We're going to take that plan, do, check, adjust cycle, and instead of one giant one, we're going to have many small ones. And we're also going to bake as much into that learning cycle as we possibly can, including things like compliance, which I'll touch on right towards the end. So small batches, and we're going to iterate the system forward. Large batches, and this research has been done over and over again by thought leaders like Don Reinertson and Tom Mary Poppendink on the difference between large batches and small batches. They have known characteristics. Large batches are highly variable. They're not predictable, especially the higher utilization that you have in your development capacity. And so if you're running everybody 100% capacity and you're running large batches, the chance that you're going to find an that's going to cause a severe project slippage is extremely high. By comparison, when they researched other systems that are designed to develop in small batches, what they found is small batches go faster. They're more predictable. They have lower variability. And even when the utilization gets higher, that utilization has less of a negative impact on the batch size than with the large batch. Next, we're going to establish cadence and synchronization. Again, I've alluded this to a couple of times, but now we'll focus in. What are we talking about? On slide 30. So cadence is this idea that we're going to have a rhythm. And that rhythm, and a team rhythm, it could be, weekly to bi-weekly, whatever the case may be. Or I'm going to talk about the program itself. The program has a rhythm, and it's typically a 10, 12-week rhythm that says we're going to commit into what we're delivering inside of that window. Everything beyond that is a forecast, but if we can manage our scope to this, we can make some decisions. We can manage dependencies and integrations much better. We can be much more predictable in what we can actually tangibly deliver within that time. The further out we go, it's harder for humans to really get their heads around, very large numbers, the law of large numbers. It's hard to do that when we're predicting and estimating in smaller batches. We do that much better. So this enables the small batch size. It schedules the integration point. So all of those different suppliers know exactly, when that point in time is that they're going to have to integrate. Now that only happens if they do the other half of the picture here, which is the synchronization. It doesn't help if everybody's doing 12-week time boxes for this iterative development, but they're not aligned together. That doesn't allow us to integrate the next component in the fuel system with the engine system if those integration time points are completely different. So cadence is that rhythm, synchronizes everybody has the same rhythm. And together, that's how we basically are sprinting an entire system forward. And again, we're seeing this used effectively even in physical systems, not only in the government defense space, but in many commercial spaces like automotive and telecommunications and others that are also dealing with physical systems. So what you end up with is a picture that looks like this. And it's this recursive fractal picture, right? So every individual team has these tight plan, do, check, adjust loops, but they contribute to some subsystem. And that subsystem has a longer window, but it too is iterating itself forward. And then the entire solution, based on periodic, let's integrate everything together and see where the whole solution is, also has its larger fractal plan, do, check, adjust cycle. Again, this is the key to alignment, integration, dependency management in very, very large, complex systems. And that takes us to next, apply continuous integration. We kind of coined that term. What we mean by continuous. So this is, again, one of those friction points between how software systems work and how physical systems work. In a software system, we have the idea of continuous, integration. As soon as somebody writes code, checks in code, it goes through the CI, the continuous integration and deployment platform, which means there's a lot of automation to run a bunch of tests, to compile the code, to assemble it, to build it, to make sure that it's working, and it can all be done in kind of a hands-off way. And so if you're building a new piece, the system can test whether or not your piece plugs in with everybody else's piece, and if it doesn't, it'll reject it back and tell you where it failed, and it's a very cool thing. When you're doing physical systems, some things you can still automate. We're seeing some very cool automation in physical systems, but there are also obviously parts of the system where you're just going to have to get part A and part B, and you're going to have to physically plug them together, and you're going to have to see if that actually works. And while that sounds obvious and almost trivial, it's really not. And if you look at case studies, the one I did a few times in my doctoral program was the Boeing 787 program. All due respect to Boeing, we love them. They build great things. But if you look at the case study of that particular product and some of the delays and problems they had getting it to market, this was one of the critical failures in the program, is not having that frequency of integration, particularly of the parts. And many of the times these were parts being provided by different boutique suppliers, of not forcing that frequent integration. So when they finally did integrate, you had simple things like, one company assumed metric and the other assumed imperial in measurements, and they try to fit the parts together, and lo and behold, they don't fit. And the longer you take to discover that, the more delay and the more cost overrun you're going to have. So what we mean by continue-ish is, in a very, very big complex system, not everything is going to integrate with everything else, but you do have to understand what parts of the system do connect, and where those connections are there, those are the ones that you're going to want to integrate more frequently. Where the connections are more downstream, then those integrations are probably going to be less frequent. But you still want to have this discipline of every certain period of time, whatever your cadence is that you set, we do a full integration of the entire system. So even if we're building a jet aircraft, a fighter jet, we can say, as of today, this is where this new generation of fighter jet stands. You can see it. You can see what's been developed, what still has yet to be developed, what's working, what's not. Okay. Next slide. What that means when we're dealing with physical systems is sometimes you have to use proxies. And in software land, we call that stubs. That language may also be used in physical systems. But it's basically a proxy, a placeholder for some part of the system that has not yet been developed, so that you can test an integration. Now, obviously there's a trade-off here, because it's always a balance. But if you wait for the actual subsystem, the cost of delay can get really high, and the risk of not discovering something is high. But also, if you wait too long to hold proxies as the validation that something is working, then you run the risk of inaccurate feedback, that proxy didn't actually totally reflect what the true final component was going to do. And so there's some validity issues with that data. Somewhere in the middle, you have to find the balance, and there's no one right answer. Just be aware that this is a common practice. It's just a reality of building physical systems, and every program has to find its trade-off of how long it can go before it actually has to integrate the actual piece of component, whether it's hardware or software. The other thing that we see is aligning both functional and physical roadmaps. So again, the idea here is understanding what parts are going to happen when, and what teams are delivering it as part of the cadence. And so the coordination that has to happen here, if you think about it, a lot of times hardware teams are are preceding some of the other parts of the system. And so there are going to be a lot of dependencies between other components wanting to know when that particular platform or component is going to be ready for delivery. And so having clear visualizations so other downstream teams know when those parts are going to be available for integration for other parts becomes a real critical part, and this is on slide 35. The next concept, be test driven. So what we're basically saying here is we've always had the V model, and there's nothing inherently wrong with the V model as you see on 37. All we're suggesting and what we're seeing happening by many organizations is this idea of shift left. Shift the V left so that the delay between the left side of the V and the right side of the V is much more collapsed. So we're testing things in much more continuous real-time fashion rather than having the delay between when the thing is written or built and when it is actually tested. And again, some of those tests may have to be against proxies early on, representations of the part like 3D printed parts, but as soon as you can get the real part in, but at least you got some learning from the proxy part that may save you some time in building the real part. You find things that may have adjusted what you actually intended to build. And that's an important part of this process as well. And I think this is the last one, continuously address compliance concerns. This is slide 40. And what we see, and we see this happening with great increasing frequency all over the place, especially in the government, because compliance is such a huge part of the overall life cycle model. And whether that's a security compliance thing, an ATO type of compliance, or whether it's the other safety kind of check tests of systems. And we're absolutely not suggesting that we shortcut any of those tests, not at all, because we know that the human cost and the social economic cost of failure of some of the systems that we're building can just be unacceptable, right? But we think the idea of having a continuous compliance model actually makes that compliance more sound. Why is that? Because the fundamental concept here is we're going to build those compliance checks in as we go along much more frequently than we have in the past. So could that be things like you actually have compliance people and teams and individuals working daily with the systems, the parts, the pieces as they are being built, doing their checks, checking test results against specifications, looking at the data, making sure that all the tests that need to be run have been run, instead of waiting downstream for a large checkpoint.
Got an IP change on the machine there. I just gotta grab that information.
Someone may want to mute their phone. We're hearing in the background. So you want to build that incrementally. And I've actually talked to compliance officers and asked them, I did this out in Silicon Valley a while back, and asked them, would you rather have the ability, do the way you're doing it now, or would you rather have the ability to work more frequently with the system as it is being built, so that you can see smaller pieces of the system and give more immediate feedback? And they said, absolutely. They would absolutely prefer to do that because they feel like they can actually contribute more value to the overall solution being built when they can catch things while they're still visible in smaller pieces, and they can actually contribute to that being corrected before it goes out as a defective part. And so that's the idea here. So we're going to do this iteratively and incrementally, continuously through the system. Does that mean that we eliminate all the final, check rides and flight tests? Of course not. We are still going to do those things. But what we find is that the more this iterative compliance is done along the way, those final checks become more non-events. The people and the teams go into those events with high confidence because the thing has been validated and tested so many times by the time they get to that point. And because compliance has just been baked into how we work and how we build each part of the system, that they're very confident that those final checks are going to pass with flying colors. So that's it. That was a fast run through that. I wanted to get through all 10. It's more, we didn't go deep into any one, but I wanted to hit the mark at 10-minute till to have at least 10 minutes for questions. And I think we hit that. So with that, I'm going to pitch it back to I guess, Miriam. If you've been monitoring the questions, I'll be happy to answer anything that we have from the group.
Thanks, Steve. Oh, I was going to say we didn't have that many questions listed, but it looks like Rada Michelle has one.
Sure.
Actually, since this seems a bit more complex, if you'd want to mute yourself directly, you could ask your question. But let me run down. It looks like there's a two-part. So just reading this straight out, chewing one's food into smaller pieces generally aids more efficient and effective digestion, pretty straightforward. But those internal biological processes are already well-established, efficient, and effective. So first point, I am wondering who, what, where the more frequent, but perhaps now smaller pieces of cost are being considered with each system-related decision that will be made during the proposed system development process. There's a critical need to understand and assess technical debt and its accrual during systems design, systems development, systems procurement, systems maintenance, and systems sustainment to facilitate evidence-based decision-making leadership into the enduring future of systems operation, particularly with respect to systems with potentially longer life cycles than typical commercial systems, military space, etc. There's a second point, but maybe we'll start with that.
Yeah, there's a lot of pieces to that. Let me pick out what I think the crux was, and whoever asked the question can certainly follow up if I miss the mark. One of the things that we do see, and it's a legitimate concern, and it's just one that we have to work through over time. And that's why a transition to this new model is absolutely not an overnight thing. This takes years for this shift to take place. And one of the reasons why is, if you think about all of our cost modeling, all of our ways of estimating the full life cycle cost of the new system, on the government side, to get them proposed, to get them approved and authorized by Congress, and before we ever build anything. And then from a systems builder's perspective, how do we know what to cost out and what to propose when we're going after that business? All those models, all that historical data is really based on our previous way of building things. And we know how critical, and we call it yesterday's weather, even in Agile, it is the previous systems that we build really do inform, give us a lot of the data that we use to project the cost and the process for building the next systems. Well, when you're making that shift, you don't have a lot of that data to understand what will the effect be on my modeling algorithms and models if I now have the ability to develop this system differently. So is it going to cause maybe an uncomfortable period where some of those historical patterns don't work so well when we say, hey, we want to develop this in a more iterative fashion? It does. And I'm not going to sugarcoat that, and that we see that as being one of the most difficult things to work through, especially for those parts of the organization that are kind of a few levels removed from the development organization. So the finance organization and other parts like that may not fully understand what this shift is and why it's affecting the way they're estimating and forecasting. But what I have seen come out is that if you can navigate your way through that temporary choppy water, what comes out the other side is something that's actually far more predictable. predictability is the real currency and the real benefit that we're getting from this. And predictability comes because what we're doing is we start with the scoping parameters, the costing parameters, and design parameters at a higher level of abstraction, and we get to the more specifics as we learn through the development process and as we make adjustment after adjustment after adjustment, which means the final output is going to be arrived at faster and more accurately with fewer waste in time and waste in cost because of redo and technical debt. It actually helps the technical debt problem because you're able to catch things sooner rather than later in the process. And we know the long litany of programs that in some cases have been canceled entirely because of things that were found so late in the process that it was actually more cost effective to cancel the whole program and start over. And that's what happens when we push that checkpoint down the road. So I know that's a bit of a rambling and may not have hit the target on the answer, but I just wanted to acknowledge that when you're making the transition, and this is true both for the supplier as well as for their government counterpart, this is something that both industry and government have to go through together as a learning process. And if you talk to some of the programs like the F-22 or some of the space programs or some of the satellite programs that are already down this path, they'll be the first ones to tell you, yeah, we kind of had to rebuild our process models for this, because this does change both how the government plans on its side and how the supplier plans on their side.
I appreciate that. That definitely probably hits some touch points for for SERC experience. Just continuing off of what Ronald Michelle had written, it was when using DevOps, Agile, Lean, what methodology and metrics are utilized to maintain visibility and manage cyber-physical system development decision? Looks like accountability, but it started getting cut off. And it looks like you was mentioning associated costs, the accrual of technical debt that may likely be incurred. I apologize for butchering the question. I seem to miss some of it.
Yeah, no. So accountability, and I totally get it. When you're working in the government space, and I work with different panels and groups, like the GA group that's building the new audit guide for Agile programs, and talk with folks from GAO and OMB and all the different agencies that are very, very concerned about how do we do this new way of working and still make sure that the government is getting a fair product for a fair price, that there's visibility, accountability into the spend, so we avoid the overrun and so forth. And certainly from our history, they have every reason to be concerned over that. Here's the key thing, and this is not just something that's just safe or just DevOps or just physical systems. Agile and Lean and DevOps in general, one of the key differences and ways of working that has to shift is industry and government have to work closely together in partnership as the system is being developed. The days of having massive specifications, throwing it over the fence, and then coming back later, that just does not work anymore. And we see that on the programs that are doing this, that where the government proponent, the functional counterpart that has the fiduciary responsibility for the program, and their industry partners that have the technical expertise to build the solution, work closely hand in hand, day in, day out. And so they're not looking at a report to tell them how their program is going. They're seeing it, and they're having the ability to input. They're having the ability to interact with their industry partner as they come into unknowns, as they reach forks in the road where decisions have to be made, where we could go option A, option B, or option C, and they have a voice in that process, and they're providing feedback and the demos as to whether or not what was demonstrated is hitting the target or not. So those things that in yesterday's way of working were largely driven by lots of reports and crunching of numbers to see if, are we being accountable to the dollars that are being spent, is now being done in much more real time. Reports are still there, but they're backed up by the actual physical evidence of something that can be demonstrated. And the people who have that expectation of accountability are much more involved and are speaking into whether or not that's on target or not as it's being developed, not having a long delay to some point in the end where now it's a crisis. Now there's a lot of rework and a lot of finger pointing, a lot of blame game because how did that happen? We want to try to avoid that, right? And so this becomes a collaboration the whole way through. Again, that's a big shift. Not every agency program is historically been built to work that way. But if you get through that churn and choppy water of figuring out how to do that, that really is the most successful way. It really is a true day-to-day collaborative, communicative partnership. And that's the best way to make sure that the accountability and traceability is there.
Yeah, excellent points. Sort of bringing this back and almost personal question of mine, Michael McLendon is asking, early in the presentation, you differentiated Lean, Agile, and DevOps from systems engineering. You mentioned he recently listened to a similar presentation and the word engineering was never used. So do you consider Lean, Agile, DevOps, engineering processes and practices?
So all of those reflect different bodies of knowledge and learning. There are certainly overlaps and I think lots of synergies. They borrow from each other. So if you just look at history, the body of knowledge of Lean is born in manufacturing that goes back into the 1940s, right? And systems engineering has its own history, and Agile has its own history. DevOps has its own history. So they are discrete bodies of knowledge, but if you look at modern systems development, especially physical systems, they draw upon all of these disciplines and all of these bodies of knowledge. If you go into the F-22 shop, you're going to see all of them. You're going to see Lean, you're going to see Agile, you're going to see DevOps, you're going to see systems engineering, you're going to see software engineering, you're going to see lots of different engineering. It takes all of those disciplines working together to produce the solution that the government expects. And there's some places where there's lots of crossover. Sometimes there's confusion because the taxonomies may not be completely aligned. And that's some things that we often see customers have to sort of work through. So we're all calling the same thing, we know what we're saying when we label something a term. So which discipline did that come from? But by and large, I find that, they come together in a hybrid of practices. I see very, very few, if any, purist types of programs where there's only one of those disciplines being used. It tends to be an amalgamation of many of those bodies of knowledge at play.
Excellent. So Judith Dobbin just had more of a comment saying, in defense systems of systems, we have adopted a wave model approach, which is very similar to the approach you've laid out here. Your presentation has given me some good ideas, some different language to reinforce the value of this type of approach. So thank you.
Yeah, absolutely. And again, as I tried to say a couple of times throughout the presentation, and don't want a lot of what we talk about when in the framework and in presentations like this, we're absolutely not claiming we invented a lot of these things. We do observe and learn and write and articulate it so that people can digest it and reuse it easily. I've been a PMP since the mid-90s. The rolling wave planning is nothing new under the sun. It has some different, maybe some different practice and some different ways it's done when you apply a Lean, Agile, or more continuous delivery model. But conceptually, yeah, it's something that we've been talking about in program management for a long time.
Excellent. Judith, I don't know if you had anything to add, but you're available to speak if you'd like.
Great. Yeah, thank you very much. Yeah, no, I agree. And I think that it's very interesting from a systems engineering viewpoint. the need to really open up and adapt our, what I would think of all of these as systems engineering practices, as more flexible and adaptive ways to deal with the changing shape of systems. And coming from system of systems, the idea that you've got these multiple diverse elements and teams of teams that are responsible for their development, I think just characterizes more and more of what we do. So I thought your presentation was excellent and really appreciated it. Thank you.
Thank you for those kind words. Thank you very much.
Yeah, thanks, Judith. I think these things do come together and complement each other pretty well.
Well, agree, Barry. Thank you.
Bringing sort of the human element into it, Stephanie White asks, what do you believe is the impact of humans in the loop and humans on the loop on the process you described? You spoke about the physical aspects and software aspects, but I was interested in the human aspect.
I am so glad that was asked. Thank you so much for that question. This is the thing that probably jazzes me more than anything else is, as much as we love technology, technology's not built by technology, at least not yet. Skynet hasn't made it just yet. So it's, systems are built by people, right? And we bring our peopleness into our work every single day. And what I love about this new way of working is because if you go into the bodies of knowledge of Lean and Agile, for example, Lean talks about respect for people and culture. It's part of the ethos. There's a human element to that body of knowledge. And in giving people more discretion and more autonomy and respecting the team and the team's estimate and the team's voice in what's being built, as opposed to the team just, taking, a set of specifications thrown over the fence and they have no ability to express their experience or their creativity. We find that organizations that truly embrace not just the practices, but also the culture of Lean, Agile, and DevOps are some of the most rewarding, high energy, high performance teams. Engagement, satisfaction measures go off the charts. And I've heard time and time and time again, people say once they've worked in that kind of environment, they never want to go back to working someplace that does not work in this way. And it's that dramatic of a change. So, there's an absolute tangible human effect. If you look at our case studies that we have at Scaled Agile, you see that as one of the dimensions that gets measured over and over again, is the level of engagement and satisfaction of employees when they work in this way. So it's not often the main reason an organization goes down this path. It's often, though, one of the most dramatic changes that they experience in a very positive way.
Thanks. And I know it's 2:08, so we have run over time. So I'll make this the final question by Robert Binder. Agilists object to specialized teams for dev, testing, et cetera. The better to have shared responsibility for quality. However, in the kind of systems you're discussing, specialization is necessary. And for example, integration testing doesn't make sense until after its constituent parts are ready to test as a whole. How do you respond to the objections in specialized teams?
Yeah, so again, I have to chuckle because, in the space that we work in, we often, run across some of the more purist perspectives. And most of the people that are raising those kinds of observations have never had to work in the realities of building these kinds of systems. And so they just kind of discount it. As I mentioned several parts through the presentation, when you apply these practices in a physical systems environment, there are just some things that are going to look different than if you were just doing a pure software project. It's the nature of what it is that we're building and what it is that we're doing. Now, having said that, even on physical systems, and I'm saying this as a generalization, not as a hard and fast rule, I have seen teams in a systems engineering environment still benefit from thinking about, could we eliminate delay? Could we come to a better solution if we brought other disciplines, other domains into the team instead of having the team very narrowly focused. And it's not always just dev test. It may be different engineering disciplines. Sometimes it is test. Sometimes I'm thinking of a customer I have. This is in the private space. It's in medical equipment, where they've got people who are going to be, who have their domain, their discipline is understanding the test rigor. When you have something that can affect a human being, that piece of equipment is going to have to go through, and so they have seen advantage by having those individuals with that skill set and that domain expertise work hand in hand with the teams, so that they can provide more real-time input. Say, you do know that this is going to have to be tested in this and such way. So as you're designing how it's going to work, you might want to keep that in mind, and getting some fast feedback from that kind of person more real-time as opposed to down the road is something we're seeing happen more and more, even in the systems engineering, physical systems land. Doesn't look exactly like the typical software dev test, DevOps picture that you often see painted, but we are seeing more and more of as the full mindset shift of thinking in lean and agile terms starts to really take hold amongst the teams. The teams themselves are the ones that start asking, hey, wouldn't this work better if, and we get those requests often coming from the teams themselves. Hey, can we at least get part-time access to this person? And eventually they may end up being fully integrated to the team over the time. But the best way that happens is organically from the teams themselves, being given that ability to self-organize and really be empowered to have more determination of how they're going to build the thing, and what are the people that need to come together to build it. The more they're given that voice, we do see more of those patterns start to emerge.
Gotcha. You mean potentially like including them more in that plan, do, check, adjust cycle?
Absolutely, because that's where the learning takes place, right? So it's the evaluation. If you're just evaluating, we built a small piece, we ran some things, we're looking at it through this perspective, but maybe we didn't look at through a different perspective, which it will have to be looked at through eventually. But if that person that has that discipline, that expertise isn't there in real time, then that evaluation from that viewpoint is delayed. And potentially there's a lot of rework that's going to happen because it wasn't evaluated from that perspective in more real time.
And Robert Binder, you're unmuted in case you wanted to add to your question, or if I didn't fully contribute to that. So please feel free to do so if you'd like to. And Stephanie White actually clarified her question, which was regarding the human element. She mentioned she was speaking about humans as part of the target system, not just the development side of the system.
So absolutely. But I'm not clear on maybe if you can provide a clarification. If we're talking about incorporating the human actors that are going to be a part of the total system in the development cycle, if that was the slant of the question, then absolutely yes. We've been promoting that and have seen that being done for a long time. But if that wasn't quite the question, then maybe we should clarify.
Yeah, and Stephanie, feel free to clarify. You're able to unmute yourself as well. Yeah, it almost seems like both of those questions tie similarly together, if I'm understanding it correctly as well.
Yeah, I think what you want to do is involve the end users, whether it's the pilots or the maintenance people or whatever. So that...
Oh, absolutely. And in fact, I was working on a system for customs and border protection. Not so much a physical system, but it illustrates the point. Is as they were building that system, they actually brought in border agents, put them on TDY orders for 6 months, brought them into Alexandria, and they were embedded in the teams because they had a perspective of the system that was being built. What happens on the border day in, day out, how they do their job. And there was a human factors piece of it that if they'd only given it to a bunch of developers to build against a set of specifications, would not have had the flavor, not have had the color of how they were actually going to interact with the system. And it had a dramatic effect on both what ended up being built and how effective the system that actually was built was in the end.
Excellent. So since we're at 2:15, if there are any more questions, I know, Steve, you left your information listed here in the slide deck, as well as available on the website. So if it's okay with you that people can direct their questions to you via email?
Absolutely.
Perfect. And Barry, I don't know if you'd like to mention our next upcoming series in the CERC Talks.
Yeah, the next topic is distributed autonomy. That you're having a lot of drones or various kinds of robots or things like that are bouncing around, and it's hard to tell or communicate with them or get them to collaborate or understand what they're going to do next, so Azad Madni has been doing a bunch of work on this and using learning techniques so that people can test hypotheses about whether the situation is what they think it is or whether there's something that is disruptive that's going on, that sort of thing.
Yeah, and he mentioned some of his prototypes are already in play and his research taking place currently. So the registration is already available for that next CERC Talk, which is taking place August 7th, again, on Wednesday at 1 p.m. Eastern Time. So feel free to register in for that now. And Steve, until they, as you mentioned, design themselves, we'll see how that works out. And sorry, just going to the next slide. Thank you again, everyone, for joining us for today's June talk. And thank you again to Steve Mayner for your presentation. Really appreciate it.
Thank you for inviting me, and hopefully we'll get to it again.
Thanks so much. Take care, everyone.
Okay. Thanks, everybody.